The sky over Honolulu turned green. Not a storm, not lightning, not any natural phenomenon that could be named or cataloged or explained away. For 6 full minutes, the Pacific sky burned with colors that had no business being there. Rippling curtains of emerald and crimson arcing across the stars like a wound in the atmosphere. 800 miles away, in the cold dark above the ocean, the United States government had just detonated a thermonuclear warhead in space. And absolutely nothing went as planned. Hotels sold tickets for rooftop viewing parties. Newspaper headlines promised a show. "Nuclear blast tonight may be dazzling," they printed. And the tourists arrived in cocktail dresses and linen shirts, cameras raised, faces tilted toward the sky. And the sky delivered. The artificial aurora was breathtaking, shimmering, vast and luminous, and completely impossibly beautiful. The kind of light that makes you feel small in the best possible way. The kind of spectacle that makes you believe humanity is capable of something magnificent. People cheered. But do not be fooled. What those rooftop crowds were witnessing was not a celebration. They were watching the opening seconds of a catastrophe that scientists would spend the next decade trying to understand. While champagne was being poured on hotel rooftops in Hawaii, something was dying in orbit. Then another thing, then another. The beauty was the beginning of the disaster. It always is. In 1962, humanity had exactly 24 operational satellites circling Earth. Every single one of them was now flying through an invisible radiation environment that no one had designed for, no one had predicted, and no one knew how to stop. Within months, they began to fail. Telstar 1, the satellite that had just transmitted the first live transatlantic television broadcast in human history, a moment that felt like the future arriving, went silent within 7 months of the Starfish Prime detonation. Britain's first satellite, Ariel 1, was rendered inoperable within weeks. By the end of 1963, at least 6 satellites had failed as a direct consequence of a single nuclear test. That was roughly 1/4 of everything humanity had put into orbit. Gone. Not due to technical malfunction, not due to design failure, due to a man-made radiation belt that now encircled the planet, invisible, persistent, and far more powerful than any model had predicted. The scientists had run their calculations. They had signed off on the test. They were some of the most brilliant minds of the 20th century. They were wrong. Glenn Seaborg, Nobel laureate, chairman of the Atomic Energy Commission, later acknowledged that the Starfish results overturned all prior predictions and that the radiation belt's intensity far exceeded anything the scientific community had anticipated. The electrons injected by that single detonation on July 9, 1962, were still being measured in Earth's atmosphere in 1968. 5 years later, half a decade of man-made radiation silently circling the planet, killing machines one solar pass at a time. This is not a Cold War footnote. This is a warning. To understand why the United States detonated a nuclear weapon in space, you have to understand how afraid it was. October 4, 1957. The Soviet Union launches Sputnik, and the fear that tears through Washington is not about the satellite. It is about the rocket, because any rocket powerful enough to put a satellite into orbit is powerful enough to put a warhead over any city on Earth in under 30 minutes. The space race gets taught as exploration, as scientific competition, as the romance of the cosmos. It was not. It was a military emergency. Enter Nicholas Christopoulos, a self-taught physicist who had learned nuclear theory while working as an elevator repairman in wartime Athens. He understood something critical. Earth is surrounded by a magnetic field generated by the movement of liquid iron deep in the planet's core, a field that extends far into space and traps charged particles in what we call the Van Allen belts. His idea was elegant in the way that only the most dangerous ideas are. Detonate a nuclear weapon inside that magnetic field at high altitude. The explosion releases a massive burst of high-energy electrons. The field catches them, traps them, just as it traps natural radiation, an artificial radiation belt. Imagine a ring of lethal charged particles positioned in exactly the orbital band that Soviet ballistic missiles would arc through on their way to American cities. Those missiles don't fly flat across the ocean like aircraft. They climb through the atmosphere, arc through space, and descend. A radiation belt in the right position would fry their guidance electronics before they reached their targets. The Pentagon moved on this idea within months. In 1958, Operation Argus detonated 3 low-yield nuclear devices between 200 and 500 kilometers altitude over the South Atlantic. The belts formed, the physics worked, the electrons spread along magnetic field lines exactly as Christopoulos had theorized, but they faded too quickly to be militarily useful, so they decided to go bigger. Operation Fishbowl, Johnston Atoll, a strip of coral in the middle of the Pacific Ocean, 1,500 kilometers southwest of Hawaii, chosen specifically because it was as close to nowhere as geography permits. The first attempt, June 2nd, 1962, the missile was immediately lost on radar. A nuclear weapon, somewhere in space, location unknown. It was remotely destroyed, debris in the ocean. The second attempt, June 19th, engine failure at 30,000 feet. The missile breaks apart, scattering plutonium-contaminated debris across Johnston Island and surrounding waters. The third attempt was July 9th, 1962. The Thor rocket carried its 1.4 megaton thermonuclear warhead to 400 kilometers altitude, roughly the orbital height of the International Space Station, and detonated successfully. Starfish Prime, the largest nuclear weapon ever detonated in outer space. From here, nothing goes according to plan. What does a nuclear explosion look like in space? Not what you're imagining. There is no mushroom cloud, no column of superheated Earth and debris spiraling skyward, because there is no Earth, no air, no material to pull upward. There is no fireball in the traditional sense, because there is no oxygen to sustain combustion. What there is light, an intensely bright flash, expanding outward in a perfect sphere, edges curling into luminous tendrils as the energy dissipates. Then, seconds later, the auroras ignite as ionized particles from the detonation collide with the upper atmosphere, visible from New Zealand, 7,000 kilometers from the detonation point. In Honolulu, 1,500 kilometers away, the sky glowed for 6 continuous minutes. But what does a nuclear detonation do to the electromagnetic environment? What happens when gamma rays have almost nothing to stop them? Here is the answer, and it is not comforting. When the warhead detonated, it released gamma radiation in every direction. Those gamma rays struck the thin upper atmosphere, collided with air molecules, and knocked electrons loose, a process called Compton scattering. At 400 kilometers, where the atmosphere is almost non-existent,